pointer.
Yeah.
Is this correct?
Good. Yeah. Yeah. That's it. Sure. Yeah. Very good.
All right, well, we made it to the end of the second day. So it's time for Nigel Hitchin to give his second talk, and this one will be about a universal moduli space. So,
Okay, thank you. So this second talk is going to address similar issues that Brian has been talking about over the past 3 days, but from a different point of view. But it was stimulated by a talk given by his collaborator Richard Wentworth in Madrid last June. So let me begin though with my basic interest in Higgs bundles. At least there's this original interest was the hyperkähler metric. And let me set the scene. So we have a usual situation of curve of genus bigger than 2, Higgs bundles. So a Higgs field is a section of the endomorphism bundle twisted with the canonical bundle. And we've got the Higgs bundle equations here, which you can equivalently state as being that this expression here is a flat connection for all theta. In other words, if you look at the flatness condition for this and look at the individual Fourier components, then you get the holomorphicity of phi and this equation here. So what we have is the hyperkähler metric on the moduli space, which comes from interpreting it as an infinite dimensional hyperkähler quotient. And so we have our complex structures I, J, and K, where I, my terminology is the moduli space of Higgs bundles, and J will be the moduli space of flat connections, the character variety. So the non-abelian Hodge correspondence tells us that we have this relationship. We have 2 different complex structures on the same underlying manifold, both with complex structures, but both complex, but different as complex manifolds. So it's really the symplectic aspect of it, which is fundamental for me in this. So MI, the Higgs bundle complex structure, it has the symplectic form, the Kähler form, omega-1, and then omega-2 plus I omega-3 forms a holomorphic symplectic form relative to the complex structure I. Now, complex structure J, so this has the complex symplectic form, the Goldman form, and this is in the hyperkähler interpretation, this is the complex form omega-3 plus I omega-1. So omega-1, the Kähler form for the Higgs bundle complex structure, in my convention here, becomes the imaginary part of the holomorphic form. So there may be an I here, but somehow I like the symmetry of I, J, K and cyclic. What we also have is an isometric circle action, rescaling the Higgs field by e to the I theta. This is holomorphic in complex structure I and preserves the Kähler form. So it generates a vector field, a Hamiltonian vector field, X, with respect to omega-1. And the function F is basically the norm squared, well, my convention is minus the norm squared of the Higgs field over 2. And the other role in which this function F plays, the other role it plays, is it actually determines the Kähler form omega-2 by this formula here. So it's a Kähler potential in complex structure J, but it's a moment map in complex structure I. So the upshot of this is that if we start with the character variety, with its complex, let's think of its symplectic structure, omega-3 and omega-1 and its complex structure J, then if we know this function F, then we know everything, because given J is known, so we can get omega-2 from the formula dJ dF, and then we can use omega-2, omega-1, and omega-3 to generate the whole hyperkähler picture. So what one wants to understand is the variation of the Higgs bundle moduli space as we vary the complex structure on the curve. This is the essential feature of these universal moduli spaces or joint moduli spaces. And so we have to understand the behavior as we vary over Teichmüller space, which is a complex manifold. We're going to regard it as a complex manifold, not as a symplectic manifold. and it parameterizes complex structures on C. And everything I do will be natural, and so it will be invariant under the mapping class group. And so what it comes down to then is that this function f, if we now think of it as a function on the character variety times the Teichmüller space, then this determines all hyperkähler metrics for all complex structures C, and so in some way determines the geometry of the whole family. So that's my point of view. And I should say before saying this that, okay, I think later on we're going to hear from Luis on another aspect of this universal moduli space. We've heard a lot from Ryan based on this joint paper here. And just to point things out, so what I'm doing is starting with the character variety times the Teichmüller space. So I'm not starting with the Higgs bundle moduli space as a complex manifold. If I do that, then the isomonodromic leaf of the foliation consists of the Higgs bundles defining the same point in the character variety. I'm looking at it from the opposite point of view. I'm looking at trivialization. I'm looking at, if you like, the product the product of the character variety in Teichmüller space, and I'm going to basically reconstruct, using F, I'm going to reconstruct the holomorphic family on this. So I'm going to go backwards, going to go from this, rather than thinking of an isomonodromic foliation on the Higgs bundle moduli space, I'm going to start with the isomonodromic foliation, if you like, and construct the holomorphic structure on the twistor space, on the universal family. So that's the aim. So everything depends on this single function f. And so I'm not using any of the equations of any of the actual metrics which involve, it's just a property of the moduli space that I'm going to use. On the other hand, there aren't many moduli spaces that I know of for which you can do this. Okay, so let me talk now about the language in which I'm going to do this. So just let me recall for you that an Riemann connection. If we have a C infinity fibration of manifolds, where each fiber is diffeomorphic to a manifold M, then an Riemann connection is a horizontal subspace of the tangent bundle of the total space. But we want to think of that in terms of gauge theory, if you like. So you can think of this as having a connection on a principal bundle where the structure group is the diffeomorphisms of M. And then this happens to be the bundle associated to the action of the diffeomorphisms of M on M itself. But if you take the adjoint action, the action on vector fields on M, then you have a notion of covariant derivative. So what does it mean? So the bundle that you're acting on is the bundle of C infinity sections of the tangent bundle along the fibers as an infinite dimensional bundle over the base. And how do you define the covariant derivative of a vertical vector field? Well, if you take a vector field on the base, if you lift it horizontally and take the Lie bracket, then that's the definition, if you like, of the covariant derivative of vector fields along the fibers. And so in our case, so we're going to start with this product. So that's a flat connection, right? And it preserves, because J, complex structure on the character variety, and the two symplectic structures, omega 3 and omega 1, are constant, then we can say that that trivial flat connection preserves these J, omega 3, and omega 1. And I want to focus on omega 1, on this symplectic form, omega 1. So it acts on Hamiltonian vector fields with respect to omega 1. And so we can think of, so what is its action there? So it's very trivial. So I'm writing it now as the covariant derivative nabla b acting on the function. It's just the derivative of that function in the direction of the base. So I've got a product. I can look at the derivative, the vertical derivative, and look at the derivative in the direction of the base. And that I want to think of as the action of the diffeomorphism. So now it's essentially an extension of the diffeomorphism group. you say, well, sorry, it's an extension of the Hamiltonian diffeomorphisms by the actual functions. We need the Hamiltonian function. So now, in the last lecture, I told you what the variation, the first variation of this function f was, as we varied, we took a tangent vector in the basic directions. So, okay, let me just say that I'm calling Teichmüller space here calligraphic T, I'm writing as B. That's because I find it very distasteful writing T of T, tangent bundle of T, and so forth. So I'm afraid that's my convention. So what did we do? Yesterday, we calculated what I called f dot, which was the variation in f as we go in a tangent direction in Teichmüller space, and that turned out to involve the quadratic term in the integral system. And so we had mu representing a class in a direction in Teichmüller space. So the tangent bundle to Teichmüller space at a point given by a complex structure C is given by a vector in the first cohomology with values in the dual of the canonical bundle. So I want to think of taking a vector there, and then the direction, so the derivative of f in that direction is given by, if you like, the interior product of y with a one form in the base. So my f dot depended on the direction. So now I want to say that basically beta, a section of the pullback of the cotangent bundle of the base, is defined by the covariant derivative with respect to this flat connection of the function f. Okay, so now we have a circle action along the fibers, and that circle action preserves omega 1, but it doesn't preserve the flat connection. So we can take that flat connection, that product, and we can deform it by the circle. So then we get a family parameterized by the circle of flat symplectic connections. And, well, connections form an affine space. The circle is a compact group, so we can average over the circle and get an invariant connection. So this will be given by the flat connection nabla B plus C, where C will be I want to think of it now as, I want to think of this covariant derivative as acting on functions. So if you like, my Lie algebra, if you think of it this way, to engage theoretic terms, I have a bundle of Lie algebras. That Lie algebra is the space of real functions on M, thought of with the Poisson bracket as the bracket. Poisson bracket given by symplectic form omega 1. So C is, I want to think of this as a one form with values in the Lie algebra. So it's a one form with values in functions. That's the same thing as a section on the total space of the pullback of the cotangent bundle. So now, if I want to take the covariant derivative with respect to this new invariant connection of a function h, then it's the flat connection dbh plus the bracket, Poisson bracket of C, that function h. And so this is my connection. So it's a symplectic connection, but it's not flat, as we'll see. So, but we need to determine what this C is. Yeah. The vertical bundle is functions. So it's just, yeah. If I want it to act on a vertical vector field, I take the Hamiltonian vector field of that function in the vertical direction and take the Lie bracket. Or if I want it to act on tensors, then I take the Lie algebra. So I have to do that again. I take the derivative in the vertical direction, apply the dual of the symplectic form and get a vector field and take the Lie bracket, whatever tensor. So that's the way it's going to act on tensors. But it acts on functions as well in this way. And so, okay, so we have to investigate the properties of this invariant. So first of all, omega 1 was constant with respect to this product. And so that means that the covariant derivative with respect to the flat connection is 0. So if we now think of, so f, remember, is the moment map for the circle action. So if I now look at the covariant derivative of the Poisson bracket of f with h, then I know that Poisson brackets are preserved by this, by the flat connection. So I've got the formula there. And what that means is that the Lie derivative of the flat connection with respect to the vector field x generated by f is equal to the Poisson bracket of beta with h, okay? And so, okay, that's one equation. I know what the Lie derivative of, I know to what extent the flat connection is not, well, where this Lie derivative is non-trivial. But now let's look at this. So beta was the real part of an imaginary entity. So, and the scaling action of e to the I theta, it acts as e to the 2I theta on phi, because trace phi squared, of course, is transformed by e to the 2I theta, where we rescale phi by e to the I theta. So if we take the Lie derivative of that action, you see that the Lie derivative of phi is 2I phi. So that means that gamma is minus twice the Lie derivative of beta. And so what we get then is that, well, finally, that we know that we constructed A to be invariant. So the Lie derivative of nabla A is 0. That means the Lie derivative of nabla B plus C is equal to 0. That says that Lie derivative of C is minus beta, which is the Lie derivative of, well, minus this gamma over 2. And so, so what we see then is that the Lie derivative of C is going to be the same as the Lie derivative of half gamma. And I deduce from that that C equals a half gamma. You might say, okay, what about the invariant part, you know? But the invariant part would have disappeared because I averaged. The invariant part would have been put into the connection already. So I can deduce that C is equal to minus a half gamma. So then what I have is a connection. So I write the flat connection now in terms of nabla A plus half gamma. And now I write that in terms of this complex entity, phi minus phi bar. And now I apply e to the I theta to get my S1 family of flat connections. And now I look at the Fourier components to determine what flatness is, and I get these equations here. Okay, remember these brackets are all Poisson brackets. So if they look familiar, then, well, they should look familiar. So but let's just step back a moment and try and think what is happening here. So, of course, it's analogous to Higgs bundles in higher dimension because we have this phi equals 0 property. But where does the analogy hold and where does it fail? Well, first of all, the analogy means that we should think of this symplectic, this non-flat symplectic connection as the unitary connection. So it plays the same role in Higgs bundles as the unitary connection. So the Lie group, if you like, the Lie group of the compact group are the Hamiltonian diffeomorphisms of M with respect to the complex structure, the symplectic structure omega 1. And it's Lie algebra. Well, actually, so we're taking the Lie algebra to the function. So it's really the central extension of the Hamiltonian diffeomorphism. We have S1 invariance, which means that the connection, the symplectic connection acting on functions, commutes with Poisson and bracket with F, which means that as an element of the Lie algebra, the covariant derivative of F is equal to 0. So that already means that the connection reduces to the stabilizer of a circle inside the group of Hamiltonian diffeomorphisms. So we've got a reduction. So there's something in the subgroup, if you like, something in the compact inverted commas group, which is a circle. And okay, so now this is something which will make more complicated, more concrete later on. That the d bar part of A is supposed to determine a holomorphic structure on the complexification of the adjoint bundle. And so now let's look at the Higgs field. So this thing puzzled me at first, this phi equals 0. I thought this was a manifestation of the integrable system. But in fact, it's not, because in fact, so what is phi? Phi is a complex one form on the base, or actually a one form of type 1, 0 on the base, with values in functions. And so and the phi I is holomorphic on the base. But omega 1 is of type 1, 1. So when you have, so here I'm saying, okay, this phi is holomorphic. So I'm just restricting to an individual fiber now. So I'm not saying that it's holomorphic yet as I vary over Teichmüller space. I'm just looking at one of these phi's. But if I have the Poisson bracket, so if I have the Poisson, so basically under Poisson bracket, a holomorphic function acts anti-holomorphically because its omega 1 is of type 1, 1. So here's the thought, right? So I take the Poisson bracket, if I have a holomorphic function, I take its derivative and then I look at omega 1 ij bar, and that becomes an anti-holomorphic vector field. So holomorphic functions act as anti-holomorphic things, and so the action on a holomorphic function is 0. So that's why the Poisson bracket there is equal to 0. It's nothing to do with the integrable system. But still, it's there. And now we have the S1 action, which I think in the context of Higgs bundles, we see that the S1 action acts on the Higgs field as e to the I2i theta, which means, if you like, if it were finite dimensional, this Higgs field would be nilpotent. But anyway, this is what we would call, how I should put it. If there were a moduli space and we looked at the C star action, we would be looking at a fixed point of the C star action, and then we would interpret that as a variation of Hodge structure. But if you think about it, this is a variation of Hodge structure. It's just a variation of non-abelian Hodge structure. So what are we doing? We're looking at the character variety, which is as Carlos started all this, you think of the structure of the Higgs bundle with this property on the character variety as being a non-abelian Hodge structure. And so this is basically a deformation of the Hodge structure in this non-abelian context. So in that situation, it's perhaps not surprising that the formalism is the same as the formalism for Higgs bundles with nilpotent Higgs field. So we also have an invariance by phi going to minus phi, which is equivalent to some real structure. So in any case, so the Lie algebra, if you like, breaks up into odd weights and even weights. So that's the analogy. And it looks so I should say that this phi is going to be the capital theta that Brian was talking about. On the other hand, there's a difference. So first of all, my S1 family is a family of unitary connections. In this analogy, these were all symplectic, these were real connections with structure group Hamiltonian diffeomorphism. So that's like saying that we have a circle-valued family of flat unitary connections. So that doesn't happen in the usual Higgs bundle theory. And the reflection of that is that also the involution, the real structure on the Lie algebra of complex Hamiltonian vector fields is just complex conjugation. Whereas in Higgs bundles, it's, if you like, it's the adjoint, which is minus the complex conjugation or minus the transpose of complex conjugation. So really, this picture is much more like the equations, those equations that I did write down yesterday as an example of something which is similar but different. So this is more analogous to looking at harmonic maps, or in this case, pluriharmonic maps into a compact group G or a symmetric space. So if you look at, if you like, for SU2, if you look at this other Higgs bundle content, this one here, then that corresponds to harmonic maps into the 3-sphere, and with into the group SU2, And with this circle, with this invariance, phi goes to minus phi. It's like looking at harmonic maps into the two-sphere. Anyway, so there's an analogy, quite a strong analogy with Higgs bundles, but it's not quite the same if we follow this analogy. Anyway, let's get back to this connection, nabla A. So first of all, so what we know is that the covariant derivative of the function f, this function which generates the vector field, is 0, and so the covariant derivative of the vector field x is 0. But also, so we can define parallel translation with the connection. So what does that mean? It means you have to integrate a time-dependent Hamiltonian vector field to give a Hamiltonian isotopy from the fiber over t equals 0 to the fiber t equals 1. So you might object to doing that because the usual existence theorems depend on compactness, but here we're in good shape because although M is non-compact, we know that this function f is invariant under parallel translation, so it preserves the bounded set. So f is a proper function, and so you can actually solve the equations using standard methods for integrating that Hamiltonian flow in a compact region, and then by uniqueness, you can extend it to everything. So that actually gives you something which is perhaps not so obvious, that because the circle action is fixed, then it tells us that fixed points of the circle action as Hamiltonian, as symplectic manifolds are all diffeomorphic. So in fact, they're Hamiltonian isotopic as we go. So for example, it doesn't have to be the fixed point of the circle. If you have a subgroup, like for example, if you look at cyclic subgroups, we look at the moduli spaces, which are invariant under a finite subgroup of S1, then their topology, they're all diffeomorphic. That is not so obvious from first principle. Sometimes, if we look at, say, -1 in the circle, then we're looking at real forms, and then that's rather different because we have an interpretation in the character variety. What about its curvature? So now this is this takes values in the Lie, so it's a two-form on the base with values in the Lie algebra, so it's the same thing as saying a section of the pullback of the a bundle of two forms on the base. So we can think of that also as a two-form on the total space, on the whole total space in vibration, just by pullback. So here's the equation that we have, and the first thing what you can say is that, well, phi here is complex linear in mu, and mu is a type 1. So this means that it evaluated on a vector field, it's a 1-0 form. So this phi bracket phi bar is a 1-1 form. So we deduce from that the curvature of this connection is of type 1-1. And so that, if you like, is kind of justification, or not a justification, but a justification for thinking that the bundle of the algebra bundle of complex sections, complex functions along the fibers has a, if you like, a holomorphic structure as a bundle over the infinite dimensional bundle over the base. But I mean, that'll be solidified when we move on. If we look at real and imaginary parts, then this part of the equations, phi equals 0, tell us that beta is equal to gamma gamma, beta gamma equals 0. And so when you go through this, you see there's another formula for that. So FA is equal to minus gamma gamma over 4. And if we look at the equation dA phi equals 0, that tells us that dB phi is, so dB, remember dB is in the flat connection, the product connection, dB phi is equal to this. So here's another expression for the curvature. It's -1/2 dB gamma. So this gamma kind of generates everything, basically. Now, okay, so we have a complex structure on the base, on Teichmüller space. So there's a complex structure on that tangent bundle, which means that the complex structure there applied to this beta plus I gamma, so this is of type 1-0. So out of this, we see that what you get out of this is that dB, IB, dBF is equal to Fi. If you go through all these things. In other words, IB beta is plus or minus gamma. So you can use these things to replace dB gamma by dB IB, dBF. So F is some kind of potential function for this curvature. But if you write it down, if you think of Ti as being local holomorphic coordinates on Teichmüller space, then you can write it down this way. So this is a Hessian, a complex Hessian of the curvature. This is an expression for the curvature. So this is sometimes called the Levy form. So what is it? It's the, if you think of F restricted to, so in Ryan's notation, if you think of F restricted to an isomonodromic leaf, then this is the Hessian of F in that leaf. So dB is the derivative in my product, but my product decomposition is the isomonodromic foliation distribution in Ryan's form. So this is one form for the curvature as a Hessian. On the other hand, we have this equation, Fa plus phi phi bar equals 0 on an eighth, which gives another expression. So phi phi bar is now, so now we if you like, we take now the Hamiltonian vector field with respect to phi and the symplectic and the omega 1 KL bar. And you see that this is a different expression for the curvature. And so what does it look like? We've got omega 1 is a positive definite emission form. We have this complex matrix here. And so this is basically a emission form evaluated on a complex matrix, and it's on each side. So this is normal. Well, it depends on your sign, but this means the usual convention. This means that the Levy form is actually non-negative. We have a positive definite emission form applied to a matrix on each side. So this is one of the things that they pay off from this point of view is that, so this is something which goes back to Domingo Toledo's work. So he proved in more general context this plurisobharmicity of this energy functional in the case of minimal surfaces. And it was revisited by Tosic, where he investigated the null space of this Levy form. And so this is something which contributes to the stratification for Brian. So what does it mean? So in this case, we see that the kernel of the Levy form is the null space of this derivative here. So that means it's the tangent vectors which are, so this might look funny. It's the inner product with respect to y of x phi, but x phi you have to think of as being a homomorphism from the tangent bundle of the base to the vertical tangent bundle. So we're taking the interior product in the base and getting a vertical tangent bundle. So another way of thinking of that is actually that this means that this Hamiltonian vector field, so it's basically another way of thinking of this is that we take the function. So if we take a vector if we take a tangent vector to Teichmüller space, so that's an element of H1 of the curve with values in K dual. Evaluate that on the trace of phi squared, then we get a function of the integral system. So what this is saying is that we're looking at a point where that function has a critical point in the fiber. So it's where the okay. Well, we might be hearing about that in some later. So each of these things has an interpretation in the situation which has been investigated before. One of the points about Tosic, so Tosic was an Oxford student, but I only got in contact with him when he was just finishing his thesis. But I rather liked one of his theorems here. because it was kind of curious. Why should you do this? So he has this, that if you look at this map from the character variety times the base into M, given by, you take the Higgs bundle interpretation, and you multiply the Higgs field by I, not -1, multiply it by I, and look at that map, then the kernel of the Levy form is the kernel of the derivative of this, restricted to the tangent bundle of the base. That just looked so unusual. So, I mean, it was neat, but I couldn't quite understand why. But it's actually pretty obvious from this. So for me, the kernel of this map is the intersection of the horizontal space of the flat connection, and it's transformed by I. But you see the family of connections here involves e to the 2I theta. So when e to the I theta is I, that changes e to the 2I theta to minus. And so we're looking at the intersection of the horizontal space of nabla A plus gamma over 2 with nabla A minus gamma over 2, which means it's the intersection is given by gamma itself, by the vector fields which annihilate it. So that was a kind of, okay, that's just an aside, really. Okay, so I guess the main purpose of this is we want to reconstruct now M cross T as a complex manifold where the fibers are the Higgs bundle moduli spaces with complex structure I. But we're going to use the function f, or this connection, this symplectic connection, to do that. So here's a statement. So we have the symplectic connection, the invariant symplectic connection, that describes a horizontal subbundle of the product. So we're going to put on the horizontal space, we're going to put the complex structure from the base, from Teichmüller space. And on the vertical space, we're going to look at the complex structure in the vertical tangent space is the tangent space of the Higgs bundle moduli space. And so it's under this, using this horizontal subbundle, we're going to put on an almost complex structure. And we need to prove that this is integrable. And what will come out of that is that the projection onto the base is holomorphic, the circle action is holomorphic, and that phi itself is a holomorphic one form on the whole space. So what is it? So you need to prove that the d bar operator, so we've got d bar along the fibers, that's given by the Higgs bundle complex structure, and d bar A, that's the A is this flat, this non-flat symplectic connection. What we need is that d bar squared for integrability, we need d bar squared is equal to 0. So there are three pieces to that. D bar squared along the fibers is 0 because the fibers have a holomorphic. D bar squared in the base is 0 because the curvature of this actually, I've said D bar B. Actually, that's a mistake. It should be D bar A there. I'm not using, so I'm sorry. You see this? That should be D bar squared A. So I've got D bar F plus D bar A. So the curvature of the connection A is of type 1, 1. So that implies that D bar A squared is equal to 0. So the only term left is is this cross term here, D bar F, D bar A plus D bar F. And so that really is what depends on the variation of the complex structure. The main point about this, how does the complex structure in the Higgs bundle moduli space vary as we vary the complex structure of C? And so the way in which I found it useful to do that is to say that to use this symplectic form, this complex symplectic form. So this defines a complex structure in the fibers because you say that one form is of type 1, 0 if it's annihilated by the top power of omega C. So we can prove that this property will hold so long as we can prove that, if like, d bar A of omega C is equal to 0. What does that mean? That means that we think of omega C as being a complex 2 form along the fibers, and we're thinking of d bar A as being the part of the d bar part of a connection on this infinite dimensional bundle of two forms. And so it's so what is the variation? So what we've seen this. So the variation is that we take a tangent direction in the base. Omega 1 and omega 3 are fixed. So the variation is given by the variation of omega 2. Omega 2 is equal to this. Maybe we saw this yesterday, actually. Omega 2 dot, yesterday we wrote as minus dj df dot. Well, now we see that df dot is, well, f dot is beta, but in a particular direction, I'm going to write it as b. And now we're looking at the action of the covariant derivative, and this now we're using the Lie derivative terminology because we're acting on tensors rather than acting on functions. And you have two parts of it. So you have the standard part from omega 2 dot, and then you have to have this part because we're using the non-flat connection. And you get this is equal to this, and anyway, you find that the 0,1 component of this vanishes, which means that this is holomorphic, if you like, in terms of d bar a. Okay, so so what can I give you an example of? I can't give you an example of the function f, but I can tell you what, I can give you an example using this example of the intersection of two quadrics. So genus 2, rank 2, odd degree. So the moduli space is the intersection of two quadrics, and what is the Teichmüller space? Well, if we think of, I'm not writing it as Teichmüller space, I'm writing it as a space which parameterizes all the complex structures. The complex structures are the mu i's here. So if you like, a replacement for Teichmüller space is the space of unordered intervals of distinct mu i's up to the modular in action of PSL2C. So we could think of that as fixing 3 of them and varying the others to get a 3-dimensional moduli space of curves. And so this phi, or this is Brian's theta, this is what it is, thanks to this paper of Beauville and the others. So what does this mean? So we're in a fortunate situation here because the formula is defined on the cotangent bundle of the quadric. But the moduli, the variation, is on basically a subspace of that. Well, really, it's a quotient of a subspace. Remember, we have to divide out by the degeneracy foliation of the symplectic form when we restrict. But so it's convenient that actually we can use coordinates on the cotangent bundle of the quadric and mu. So phi here you see is a holomorphic one form on mu with values in this in the cojoint orbit of SOC. I didn't write it down now, but actually, if you can investigate through this the stratification of Brian, but it relates to work on the degeneracy of the critical points of the function. I think I wrote a paper on that. Anyway, I think there are other papers on it which we might hear about later on. Okay, so that was looking at the full Higgs bundle moduli space. But you could look at, you can do the whole thing, I mean, for real forms, right? So if I have a real form of the group, of a complex group, then we can look at the character variety, which is the homomorphisms into the real form. We know very well from especially the work of Oscar and his collaborators that how to describe the Higgs bundles in this situation. So we take the maximal compact subgroup of G, we decompose the algebra into H plus M. The Higgs field has to lie inside the M part of the decomposition, but we still have a circle action. And so now we can look at the product, the real part, if you like, times the base, and we can average the connection in the same way as before, and so we can get the same sort of picture. And so here's an example. So suppose we take SL2R and the uniformizing representation. So So now the Higgs bundle, so here I'm looking at the SU2 Higgs bundle rather than the SO3 Higgs bundle that Brian introduced. So the Higgs field here is determined precisely by a quadratic differential. And so what we can say is that what we get is a holomorphic structure on a bundle over Teichmüller space, whose fiber is the space of quadratic differential. So that in itself is suggestive of something of how we might understand this. But in fact, it's this phi. What is this phi? So it's a section of the pullback of the cotangent bundle of Teichmüller space. So what it does, it gives you a map, a holomorphic map to the cotangent bundle of Teichmüller space. And if you check it, you'll see that it's an isomorphism on the fibers. So what it does is it identifies this total space holomorphically with the cotangent bundle Teichmüller space. If you like, phi becomes, under this identification, becomes the canonical one form. So if you have something which fibers over a base, and you have a section of the pullback of the cotangent bundle, it defines you a map from that total space into the cotangent bundle. In this case, it's an isomorphism. And so actually, in the case of SL2R, if we do this procedure, then it's not just that we notice that this is a bundle which is isomorphic to the cotangent bundle of Teichmüller space, it's that the isomorphism is realized by this phi or this theta, whichever you like to call it. Okay, so now a lot of the motivation, I think, as I understand it, from both the approach of Oscar Luis and Marcia Garcia Hernandez and the others was related to looking at Hermitian structures, differential geometric structures on this total space. So for me, that was, I thought, is there anything that comes out of this in some natural way? And so what you can do, of course, is that you can take the tangent bundle of this product, this total space here, and you can use the horizontal subspace corresponding to this non-flat connection, and you can define a Hermitian. So the complex structure we defined by taking the complex structure on the base and pulling it back to H, and the complex structure on the fibers. So if we take a Kähler form on the base and use a Kähler form on the fibers, then this will define as a Hermitian metric on the total space. So we think of the wedge to these two forms on the fiber are isomorphic to the two forms on the horizontal space. So if we take the omega-1, if we take the Kähler form for the fiber, then if we want to put it on if we want to make it into a two form on the total space, we have to use this. We have to use a connection. If we use the connection A, then that becomes replaced by this expression here. And so this is of type 1,1, and we can pull back the Weil-Petersen form from the base, or we could pull back any multiple of this if we wanted. And then what we would have is a Kähler form. Well, sorry, not a Kähler form. What we have is a Hermitian form on the total space. So this is Hermitian, but unfortunately, it's not closed. And as far as I could work out, it's not even the D-bar closed, although that's a rough calculation. So to me, that was a big disappointment because I'm happy with Hermitian metrics which are not closed. Particularly in the context of generalized geometry. But of course, we know there are all sorts of special types of Hermitian manifolds. But somehow that, if there was some natural structure involving curvature, torsion, or whatever, then it should become apparent. But it didn't do. But so So, but what I think is that maybe this is the wrong thing to look at. So I think I wanted to reorient my understanding of this in a different way. So suppose I look at omega 1 minus a half d gamma. So that's you can build that up out of two things. So now in terms of the product connection, that's omega 1 minus a half df gamma minus a half db gamma. And so this is actually, so what we've seen is that omega 1 minus a half df gamma is of type 1,1 in this complex structure. Also, half dB gamma, the curvature FA was of type 1,1 on the base, and now we're pulling it back to the total space. So this is a 1,1 form. And if we restrict it so this is a 1,1 form, and it's closed. Because omega 1 is closed, it's the standard symplectic form on the fiber. And what it is if you restrict it to each fiber, it becomes omega 1. So it's basically the curvature of a unitary connection on a holomorphic line bundle. So it's a holomorphic line bundle on this total space, which restricts on each fiber to the holomorphic structure given by the line bundle with curvature omega 1. I'm assuming that omega 1 is integral, multiplied by some 2 pi. So it seemed to me that this was more the context of this form rather than the one I was trying to look at in terms of metrics. So just to finish, that I would say that if you look at the formula, what we're really doing is using this flat connection. But if you look at in geometric quantization, if you look at this pre-quantum line bundle, so you have a symplectic form, you regard that this as a curvature of a connection on the line bundle, on a complex line bundle, it doesn't have to be holomorphic yet, on a complex line bundle, then the point is that functions act on sections, on C infinity sections by this formula. So you take the Hamiltonian vector field and take the covariant derivative, and then you add on IHS. So this is, if you like, the Lie derivative of H acting on S. So, Lie derivatives are like, the difference between the covariant derivative and the Lie derivative is a Higgs field. Anyway, it's the moment map here. So what we've got here is that in looking at this picture, what we've got this symplectic connection, which is a connection on the algebra of Hamiltonian functions. And so it's basically the curvature I wrote down it involves the action of this connection on L. So we can write down that connection in terms of, if you like, d bar A plus its action on the connection, the Hamiltonian connection. And so what you can understand then out of this is that but what the holomorphic sections of this line bundle on the total space, on the full family, the universal family, is given by two equations. One, obvious, it has to be holomorphic along the fibers. The other is this equation here, which involves, in fact, the 1,0 derivative of S along the fibers. So, but it's a natural context in which to start to think about how one might quantize this line bundle on the Higgs bundle moduli space. Well, by using a Kähler quantization. In other words, trying to find a flat connection on sections of this line bundle, which are, they're infinite dimensional, holomorphic sections of this line bundle as you vary over Teichmüller space. It's not, this alone is not sufficient to do it, because our experience with doing it on the moduli space of stable bundles certainly tells us that we need to use the integrable system. We need to use the Poisson commuting quadratic functions in order to find that projectively flat connection. And what I've used today, although I've had Poisson brackets, I've never used the integrable system at all in terms of that holomorphic Poisson bracket. So quantization is going to involve more than this, but this might be a framework to begin it. So that's a point at which I'd like to stop.
Any questions?
I might have missed it, but are they any PDEs that F satisfies that I?
F, this curvature here?
No, your generating function. The original F.
Well, yeah, okay, so of course, because how shall I put it? In yesterday's talk, I gave you an equation for the semi-flat version, right? So if you look at the, I mean, this procedure works for the semi-flat hyperkähler metric. And yesterday I had a slide which it gave a nonlinear equation for F in that context. So, I mean, there's no simple equation, I think, in this situation that it satisfies in the same way. But clearly it has to satisfy an equation in order for the, in order for it to, how should I put it? You construct a two-form out of it, dj, df, and then you have to check all the identities, right? The identities on the algebraic identities on those two forms, or else you invert one of the two forms and you look at the ion. So there are nonlinear relations there, but okay, but I would say that there are algebraic relations on the second derivative, and that's essentially what in the semi-flat situation that was something we had the second derivative, and we had some bilinear expression involving
it. So here you are talking about the quantization of the moduli space of Higgs bundles. Some people have studied the quantization of Teichmüller space.
yes.
So is this suggesting maybe that it would make perhaps sense to discuss the quantization of the universal moduli space of Higgs bundles?
Well,
so what procedure should we, because it's not, you don't have a Kähler structure.
Yeah,
But you may have a symplectic structure.
if I'm going to use this, I'm going to use the function f, which is undetermined. I mean, it's not like I could write down what f is. I mean, but it's true that might be a good place to start. But once one has the right formalism for this, in other words, I should put it. If one's going to look at Kähler quantization of this space, then we're going to look for some kind of operator. Maybe it's a second order operator again, or some kind of heat operator. But then when you restrict it down to, but on the other hand, so what happens for, let's say, so we're looking at a different fixed point of an involution. So that if we look at moduli space of stable bundles where we know how to do it, then we don't have commuting vector fields there, but we have commuting tensors, symmetric tensors. And so to convert, on the other hand, if we're doing it on the Higgs bundle moduli space, the objects that commute are these vector fields. So somehow one has to use the vector fields in some form. But when you come down to something like stable bundles, you have to look at maybe derivatives of these in the normal direction to get symmetric tensors. Maybe the same thing will be true for Teichmüller space. I mean, it's not a fixed point of a circle action, it's a fixed point of an involution. But maybe because of that involution, the most obvious things, the vector fields are not going to be, well, they're not going to appear there, but something similar to some symmetric tensors. I mean, it's possible that one can write something down, yeah, some kind of heat equation. But I mean, the first thing is to try and do that on this context. I mean, essentially this d bar a, like because, okay, d bar a basically defines a connection on this infinite dimensional space of holomorphic line bundles, but it's not flat. That f actually obstructs it. I mean, there are no cross terms in that curvature, which means I think that it does give you I think the curly DA part, the curly DA part of the connection, I think acts on the whole thing. But it's not flat. And as I'm saying, that we have to introduce the commuting vector field somehow to do that. But I think, you know, but I mean, first of all, this issue about it's an infinite dimensional space, can you do it? But we know already from this work on the equivariant Verlinde formula that you can break up those sections into finite dimensional pieces according to the circle action. The circle action will not be preserved by the flat connection in the same way that this non-linear flat connection doesn't preserve the circle action. But nevertheless, the circle action will help to do any analysis which is required. So it's a project, but I'm not sure, at this point, I'm not sure what's going to happen.
Yeah, would this be related to the Bailenson-Drinfeld thing about quantization of the Hitchin system?
Well, well, they're looking at commuting differential operators on the space where, I mean, okay, in the moduli space of stable bundles, if you look at a line bundle of negative degree, then there are no global holomorphic sections, but there are holomorphic commuting operators. That's true. Second order differential operators. I've not yet decided, I've been experimenting, but I think, you know, when you read Witten's approach to quantization, then everything is modeled on quantization of an affine space, and there the projectively flat connection is still determined by a second order operator. So I suspect that we're going to use these commuting vector fields to define some second order operator to define a kind of, there's well, second order in terms of the function. So it might be first derivative of the vector field. So I'm not quite sure, but I don't think that the situation that they're looking at arises here, because we've got their commuting holomorphic differential operators, which are basically the same thing as the quantization of these quadratic functions. The quadratic functions give you the commuting vector fields. I don't think, I mean, you know, you can look at actions of, well, then you'd want to find, any analog of that would be looking for a holomorphic action of these vector fields on some line bundle. But on the other hand, I should say this, that, I mean, it's a good point that on each fiber, actually there's an obstruction to lifting one of these holomorphic, commuting holomorphic vector fields to act on the line bundle. So that, in other words, if you take a holomorphic vector field coming from the integral system, you take the interior product with the Kähler form on each fiber, then that's non-trivial, and that's basically the obstruction to lifting the action to local space. So that you can't just use that holomorphic line bundle and then use the action of Z on it. So I think it's something different. I think there was a question.
You mentioned this analogy between S1 actions and variations of hot structure.
Yes.
Is there a way to interpret equivariant localization theorems in terms of variations of hot structure? I think in this context, the localization is being done for this. I mean, these equivariant Verlinde formulas is basically, so you look at the circle action on sections of this line bundle, you reduce that to some calculations on fixed point sets. I think this work of several groups, I think that's where the localization appears. I don't think it's so much in this. I mean, that's all going to happen on one fiber. I don't think it relates so much to this picture.
Any other questions? Well, if not, let's definitely thank Nigel again.
Yeah.
The P is like